Hi, in this video, we are going to talk about a simple experiment called the Mach Zehnder interferometer. And this is similar to the double slit experiment that we looked at. However, this will be simpler because the possibilities in the double slit are in the continuous domain, whereas this will be more of a discrete type of situation, which will be easier to explain. So again, this experiment actually, the intention is to show the weird behavior of quantum mechanics. And let's dive into it. So the setup is the following. You have a, a source as before, maybe a source of photons or something, and then you have a beam splitter. The source, this is a source. This is beam splitter, so it's, and then you have these mirrors. So you have mirrors which just reflect the light, and then this is mirror 1, mirror 2, and then we have another beam splitter over here. So this is the second beam splitter. This is beam splitter 1. And then finally you have these detectors over here. So this is these are two detectors. So this is detector 0. This is detector 1. And so when the light enters the beam splitter, it sort of gets split in two possible ways, right? And I will call this path as path 0. So this is the whole path is path 0. And this is path 1, right? So there is a difference in the classical and quantum mechanical behavior in this experiment. In the classical space, if we have such a setup with the source being modeled by a classical in a classical way, then at the end of it, if we measure, we get 50% probability of measuring at detector 1 and 50% probability measuring at this. So this is classical probabilities. However, if we have a quantum mechanical source, then we observe, similar to the double slit experiment, we observe some interference and we get 100% at detector 1. So this is quantum mechanical, right? Now, let's try to put some explanation on this. But before that, suppose I have a simpler setup, so this is a simpler setup with only one beam splitter. So suppose I have this source and we have this beam splitter, and we have detectors over here, detector 0 and detector 1. In this case, both the classical and the quantum mechanical situation works out to be the same. So there's 50% probability of detecting at detector 1 and 50% at detector 0, right? So the situation can be explained classically quite well. So classically, you have these two paths, right? So I'll call them 0 and 1. So the source starts in path 0, right? So you are over here, and if you draw a tree diagram, then I can go, if at the first beam splitter, I can split into two possible paths, either path 0 or path 1 with equal probability, right? So I can write this as from 0, I can go to 0 or 1. So this is the first beam splitter. Now on the second beam splitter over here, there is a further sort of split. So I can again go over here from path 0 to path 1 over here. So that can be described on the second level of the tree. So from 0 path, I can go to 0 or 1 with probability half. And from the one path, if I enter the first beam splitter in the one path, then I can also go from 1 to 0 or 1. So probability of detecting at detector number 0 is from 0, I can go to 0. And then again from the 0 path, I can go from 0 in the second beam splitter. Or I can go from 0 to 1 or from 1 to 0. So this is going to be, so I'll multiply the probabilities. So this will be, the two possibilities are going from 0 to 0 and then again to 0, that is half times half. So this, and then, or from going from 0 to 1 and at the first beam splitter and then 1 to 0. So this is going to be 1 over 4 plus 1 over 4. So this is going to be 1 over 2. Similarly, probability of detection at detector 1 is again, I will draw it with a different, so if I want to get detected at detector 1, then I will have to follow this blue path over here, which is right. And again, this is going to be half times half plus half times half, which is equal to 1 over 2. And one can describe this using a matrix. So I can say that, okay, the probability distribution, initial probability distribution is this vector 1, 0, which is equal to, is just the path being 100% or probability 1 of being in state or path 0, and 0, 1 is having probability 1 of being in state 1, then I can describe the situation using a matrix which looks like this. So if I take the transitions of the beam splitter can be described as a transition matrix. So half, half. So initially, when you are in state 0, then this matrix acts on this vector and you get half, half, which is equal to half probability in state 0 plus half probability in state 1. So this is the case when there is one beam splitter. And now, if I do it one more time, so going to the second beam splitter, I apply this matrix again, and I again get a half, half. So this is then you see that the probability of observing at beam splitter or detector 0 is equal to half, and probability of observing at detector 1 is also equal to half. right? And this matrix, such a matrix which has entries, so if I call these entries P00, P01, P10, P11, so these are transition probabilities. So P00 is transitioning from state 0 to state 1. So P00 is transition probability from state 0 to state 0 and so on, right? So the situation classically can be described by what is known as a Markov transition matrix. And where we have that Pij are all probabilities and sum over j Pij. So all the row sums add up to 1. So this is the classical situation, can be described by this Markov transition matrix. And you can calculate the probabilities of the classical transitions either through the tree diagram or through this. So how do you explain the quantum mechanical situation? In the quantum mechanical situation, as I mentioned that when we are talking about the double slit, we talked about probability amplitudes. So in this case, the probability amplitudes are not probabilities, but the mod square of the probability amplitudes are the probabilities. So probability, I'm going to draw the quantum sort of situation in the form of a tree. So quantum source. Then we have a tree. Again, we are transitioning from 0 to 1, but instead of the probabilities, we have probability amplitudes. So this, I'm going to write probability amplitudes, which may be in fact complex numbers. So for instance, from 0 to 1, I have, so this is 0, sorry. 0 to 1, we can have I over square root of 2. And then 1, 0, 1. So this will be I over square root of 2. And now if you compute the probabilities, so if I look at the probabilities of detection at detector 0, now remember the probabilities are the amplitude mod square. So let's first compute the amplitude. So if I want to get detected at detector 0, then the paths are right. So this is going to be the probability amplitude of detecting at detector 0. So first let's calculate the probability amplitude. This is going to be 1 over square root of 2 times 1 over square root of 2 plus I over square root of 2 into I over square root of 2. And this is equal to 0. So this is detector 0. And similarly, if I want to compute the probability amplitude at detector 1, it will be, well, let me just, so how will we get to 1? Look at the green arrow. And this is going to be 1 over square root of 2 times I over square root of 2 plus I over square root of 2 times 1 over square root of 2, which is equal to I. And the probabilities are the amplitude square. So probability of detecting at detector 0 is equal to 0 mod square, which is 0, and probability of getting detected at 1 is equal to I mod square, which is equal to 1. So this is how you explain the quantum phenomena. In this case, it's simpler than the double slit because there are only two possibilities. And in this case, instead of the Markov matrix, the matrix that is given is 1 I 1 over square root of 2. And this is a matrix where Ui j mod square sum over j is equal to 1. And in addition, the row sums and the column sums add up to 1, but also the rows and the columns are orthogonal, right? So orthogonal rows and columns, in the sense that one has to apply the complex inner product, right? And if I calculate this now, if I look at this, so the path of the particle when it passes to the first beam splitter, you will see that it is 1 and I 1 over square root of 2, and then this, which is equal to 1 over square root of 2 1 0 plus I over square root of 2 0 1. So if I take the amplitude mod square, then detecting at detector 0 is 1 over square root of 2 square mod, which is 1 over 2, and probability of getting detected at detector 1 is I over square root of 2 mod square, which is also equal to half, right? However, if you have the setup where there are two beam splitters, then you have 1 over square root of 2 1 I 1, and then you have getting through the second beam splitter will lead to 1 over 2 1 I 1 1 I. So this is going to be 1 0, and this is going to be 2 I is equal to 0 I. So the probability of getting detected at detector 0 is 0, and probability of getting detected at detector 1 is mod I square, which is equal to 1. So that explains in a much simpler way the same situation that happened in the double slit experiment, except that now we have a discrete set of possibilities which are getting detected in path 0 or path 1.